Hello. Hello and welcome to this video. We will resume where we left the discussion of struct module, that is native formats. We will finish this read through and then we'll see an example of codecs and we will move on to codecs discussion after that. So native format says that when constructing format strings which mimic native layouts, the compiler and machine architecture determine byte ordering and padding. In such cases, the @ format character should be used to specify native byte ordering and data sizes. Internal packed bytes are normally inserted automatically. It is possible that a zero repeat format code will be needed at the end of a format string to round up to correct byte boundary for proper alignment of consecutive chunks of data. So we have been given an example on 64-bit machine. So L will be long, which is 8 bytes on 64-bit machine, followed by 2 bytes, but there will be padding because of alignment. So this will also occupy 8 bytes. And final L will also occupy 8 bytes. So there is a total of 24 bytes. But if you give LLH, then it will become 18 bytes because there will be no padding at the end. So data is not padded to an 8-byte boundary at the end of second format string without the use of extra padding. The zero repeat format code solves the problem. So put 0L here and you get 24 bytes. The X format code can be used to specify the repeat, but for native formats, it is better to use a zero repeat format like 0L. By default, native byte ordering and alignment is used, but it is better to be explicit and use the @ prefix character. Now we have standard format. When exchanging data beyond your process as networking or storage, be precise. Specify the exact byte order and alignment. Do not assume they match the native order of particular machine. For example, network byte order is big Indian, while many popular CPUs are little Indian. By defining this explicitly, the user need not care about the specific of the platform their code is running on. The first character should typically be less than, greater than, or exclamation mark. Padding is the responsibility of the programmer. The zero repeat format character won't work. Instead, the user must explicitly add X pad bytes where needed. Revisiting the examples from previous section we have. So we have less than QH6XQ. So Q, H, and X, and less than. So less than would be a little Indian. And we have to look for Q. Q is long, H is short, X is pad bytes, and that's it. So Q is long, and then H is short, and then you pad 6 bytes, and then Q again, so 24 bytes. So similarly, you can go ahead and look at all the examples because discussing everything will take time. The above results executed on a 64-bit machine aren't guaranteed to match when executed on different machines. For example, below are executed when on a 32-bit machine. So QQH6X gives you 24, while LLH0L gives you 12 because long is now 4 bytes in this case. Then we have classes. The struct module also defines the following type, that is the struct class, which takes a format, returns a new struct object which writes and reads binary data according to the format string. Creating a struct object once and calling its method is more efficient than calling module level function with the same format, since the format string is compiled once. The compiled version of most recent format string passed to the module level functions are cached, so programs that use only a few format strings need not worry about using a single struct instance. So the methods are similar to what we had at module level: pack, pack into, unpack, unpack from, and nature buffer, format, and size, which we discussed in previous video. So now we move on to an example on codecs. So first we discussed that why we should use codecs. So you get fine control over error handling, you can handle legacy encodings, the behavior will be consistent across Python versions, and you can stream, read, and write stuff. Your data pipeline can ingest messy external data without crashing because most data pipelines have to be fault tolerant. You can handle log generated by different systems in one place, and you can centralize the log. You can normalize text from intercepted sources. For example, in web scraping, or if you are receiving data from multiple sources, you have multiple clients and they send data in different sources. You can deal with encodings like CP1252 and Latin 1. So this example we won't be able to run, but it is just an example how it can work. So consider there is a raw data CSV file is there, and we have an output file saying data CSV. So we can read the input file and say that errors you replace. Then we read the content, and then in the content, if we find a Unicode character FFFD, then we replace that word by question mark. The other thing is that you can write this output file in this manner. The other place where it could be useful is that you can ignore the errors and do line by line processing, that is streaming. Now you'd observe that the open function call of codecs is deprecated, so instead you could use open, just open. This will work. Should not use codecs.open anymore because it is deprecated. So that is the example. We won't be able to run because we don't have raw data CSV and clean data.csv. So this is the example, and now we move on to codecs. So it's a quite long one, but we will try to go as far as possible. So what codecs does is that depending on the input encoding, it can read that particular file with that encoding and then output in a different encoding as well. This module defines base classes for standard Python codecs, encoders and decoders, and provides access to the internal Python codec registry, which manages the codec and error handling lookup process. Most standard codecs are text encodings, which encode text to bytes and decodes bytes to text. But there are also codecs provided that encode text to text and bytes to bytes. Custom codecs may encode and decode between arbitrary types, but some module features are restricted to be used specifically with text encodings or with codecs that encode to bytes. The module defines the following functions for encoding and decoding with any codec. The first method is encode, which takes an object. Default encoding is UTF-8 and errors is checked. So it encodes object using the codec registered for encoding. Errors may be given a set of desired error handling scheme. The default error handler is checked, meaning that encoding errors raise value error or a more codec specific subclass such as Unicode encode error. Refer to codec based classes for more information codec error handling. So we just go here and we have these are the error handlers: check, ignore, replace, backslash replace, surrogate skip. So we'll see this once we come here. The second function is decode. So it also takes object encoding and errors similar to encode, but does the opposite way. That is, it decodes bytes to text. Then we have char map underscore build. It takes a string. Return a mapping suitable for encoding with a custom single byte ordering given a str string of up to 256 characters representing a decoding table. Returns either the compact internal mapping object encoding map or a dictionary. Mapping characters ordinal to byte values, raises a type error or invalid input. The full details for each codec can also be looked up directly. So there is lookup function which takes an encoding, looks up the codec into the Python codec registry and returns the codec info object as defined below. Encodings are first looked up in the registry's cache. If not found, the list of register search functions is scanned. If no codec info object is found, a lookup error is raised. Otherwise, the codec info object is stored in the cache and returned to the caller. So codec info class takes encode, decode, two values. It also takes stream reader, stream writer, incremental encoder, incremental decoder, and name. So name is the name of encoding, encode, decode, the standard encoding, decoding functions. These must be functions or methods which have the same interface as the encode, decode methods of codec instances. The functions or methods are expected to work in a stateless mode. Then we have incremental decoder and incremental encoder, which are classes or factory functions. These have to provide the interface defined by the base classes, incremental encoder, incremental decoder, respectively. Incremental codecs can maintain state. Then we have stream writer and stream reader. Stream writer and reader classes or factory functions. These have to provide the interface defined by the base classes. Stream writer and stream reader, respectively. Stream codecs can maintain state. To simplify access to the various codec components, the module provides these additional functions which use lookup for the codec lookup. Get encoder looks up the codec for the given encoding and turns the encoder function, raises the lookup error in case the encoding cannot be found. Similarly, get decoder will look up the decoder function and raise lookup error if the encoding is not found. Get incremental encoder looks up the codec for given encoding and returns it incremental encoder, and similarly lookup error will be raised. And similarly for get incremental decoder, get loader, get reader will get stream reader, get writer will get stream writer, and so on. Then we have register, which takes a search function as input. Register a codec search function. Search functions are expected to take one argument, being the encoding name in all lowercase letters with hyphens and spaces converted to underscores, and return the codec info object. In case of a search function cannot find the given encoding, it should return none. Then we have unregister, which unregisters the search function and clears the registry space. If the search function is not registered, it does nothing. While the built-in open and standard I/O module are the recommended approach for working with encoded text files, this module provides additional utility functions and classes that allow the use of wider range of codecs when working with binary files. So you see the open has been deprecated and now it is superseded by open. So you should not use this open, okay? Since it is deprecated, I will skip this and move on. We should look at open method. So we look at encoded file. So it takes file, data encoding, and errors. The default value for file encoding is none and errors is checked. Return a stream recorder instance, a wrapped function of file which provides transparent transcoding. The original file will be closed when the wrapped version is closed. Data returned to the wrapped file is decoded according to the given data encoding and then returned to the original file as bytes using file encoding. Bytes read from the original file are decoded according to file encoding and the result is encoded using data encoding. If file coding is not given, it defaults to data encoding. Errors may be given to define the error handling. It defaults to strict, which will cause value error to be read in case of encoding error occurs. Then we have iter encode, which takes an iterator encoding errors and DWRs. Uses an incremental encoder to iteratively encode the input provided by iterator. Iterator must yield str objects. This function is generated. The error arguments is passed through to the incremental order. This function requires that the codec accept text str objects to encode. Therefore, it does not support bytes to bytes encoders such as base 64 codec. Then we have iter decode. It does a similar thing, but it is a decoder. Then we have read buffer encode, which takes a buffer and errors default value is none. Return a tuple containing the raw bytes of buffer, a buffer compatible object or str encoded to UTF-8 before processing and their length in bytes. The error argument is ignored. So codec.read buffer encode, if you take and you supply a byte string GTO, then it will tell you the buffer. It will give you the buffer in bytes and the length it has 4 bytes. This module also provides the following constants which are useful for reading and writing to platform dependent files. So constants are codecs.bum, bum_b, and so on. You can read it. These constants define various byte sequences being Unicode byte ordered marks. So BUM is byte order marks for several encodings. They are used in UTF-16 and UTF-32 data streams to indicate the byte order used and in UTF-8 as a Unicode signature. BOM underscore UTF-16 is either BOM underscore UTF-16 underscore B, big Indian, and BOM underscore UTF-16 underscore LE, depending on the platform's native byte order. BOM is an alias for BOM underscore UTF-16, BOM underscore LE for BM UTF-16 underscore LE, and BOM underscore B for BOM underscore UTF-16 underscore B. The others represent the BOM in UTF-8 and UTF-32 encodings. Then we have codec base classes. The codecs module defines a set of base classes which define the interfaces for working with codec objects and can also be used as the basis for custom codec implementation. Each codec has to define 4 interfaces to make it usable as codec in Python: stateless encoder, stateless decoder, stream reader, and stream writer. So these 4 functions you need to implement if you want to implement your own codec. The stream reader and writers typically use the stateless encoder and decoder to implement the file protocols. Codec authors also need to define how the codec will handle encoding and decoding errors. So error handlers, to simplify and standardize error handling, codecs may implement different error handling scheme by accepting the error string arguments. So this one is \replace. So if you see, beta is replaced by \df, that is the hexadecimal encoding, and this music string is by U266X. Then we have XML char reference replace. In this case, it is replaced by &hash. So these are the error handlers. Checked will raise encode error or a subclass. So then we have ignore, that it ignores the errors. We have replace, which replaces the replacement marker on encode using question mark, or on decoding uses question mark UFFFP, the official replacement character. Then we have \reference, replaces the \escape sequences on encoding use hexadecimal form of Unicode code point, which formats \HH, \UXX, or 8xs with capital U. On decoding, use hexadecimal form of byte value with format \XHH. Then we have surrogate escape. On decoding, replace byte and individual surrogate code ranging from Unicode point DC80 to DCFF. This code will then be turned back into the same byte when the surrogate escape error handler is used when encoding the data. You can go ahead and read the TUP 383 for more discussion. The following error handlers are only applicable to encoding. One is XML char replace, and the second is name replace. So it replaces the XML HTML numeric character reference, which is a decimal form of Unicode point with format &#num, and the name replace will replace with \n, and then within the brackets escape sequences, where what appears in the braces is the name property from Unicode character database. In addition, the following error handler is specific to the given codecs, that is surrogate pass, applies to UTF-8, 16, 32, and so on. Allows encoding and decoding surrogate code point D800 to DFFF as normal code point. Otherwise, these codecs treat the presence of surrogate code point in str as an error. The set of allowed values can be extended by registering a new named error handler. So first one is register error, which will be used to register the error handler. It takes a name and an error handler. It registers the error handling function error handler under the name. The error handler argument will be called during encoding and decoding in case of an error where name is specified as the error parameter. For encoding, error handler will be called with the Unicode encode error instance, which contains information about the location of the error. The error handler must either raise this or a different exception, or return a tuple with the replacement for the unencodable part of the input and a position where the encoding should continue. The replacement may be either str or bytes. If the replacement is bytes, the encoder will simply copy them into the output buffer. If the replacement is a string, the encoder will encode the replacement. Encoding continues on originally input at the specified position. Negative position values will be treated as being related to the end of input string. If the resulting position is out of bound, an index error will be raised. Decoding and translating works similarly, except Unicode decode error and Unicode translate error will be passed to the handler, and that the replacement from the error handler will be put into the output directly. So previously error handlers, including the standard error handlers, can be looked up by name. So first one is lookup error, which takes a name, returns the error handler previously registered under the name. Raises a lookup error exception in case the error handler not found. The following standard error handlers are also made available as module level functions: checked errors. Then we have ignore, replace, and backslash replace errors, XML char replace errors, ref replace errors, name replace errors. So these we have seen. Then we have stateless encoding and decoding. The base codec class defines these methods, which also define the function interface of the stateless encoder and decoder. First is encoder, which takes input and errors is strict. It encodes the object input and returns a tuple. Object length, output object length consumed. For instance, text encoding converts a string object to byte object using a particular character set encoding, example CP1252 or ISO 88591. The error arguments defines the error handling to apply. It defaults to strict handling. The method may not store state in the codec instance. Use stream writers for codecs which have to keep state in order to make encoding efficient. The encoder must be able to handle zero length input and return an empty object of the output object type in this situation. Decode is similar. It decodes the object input and returns a tuple similar to encoder. For instance, for a text encoding, decoding converts a byte object encoded in using a particular character set encoding to a string object. For text encodings and byte-to-byte codecs, input must be a bytes object or one which provides the read-only buffer interface, for example, buffer objects and memory mapped files. The error arguments defines the error handling to apply. It defaults to strict handling. The method may not store state in the codec instance. Use stream reader for codecs which have to keep state in order to make decoding efficient. The decoder must be able to handle zero length input and return an empty object of the output state type in this situation. I think we can stop here, and in the next video we will proceed from incremental encoder objects and finish this. It is quite big, but there are lots of things which we won't read. For example, this table we won't be reading, or these tables. So we should be able to finish this in the next video. And so next video will be day after tomorrow, not day after tomorrow, fourth day from this. So I hope that you are enjoying and finding the video useful, and you are enjoying the read through of Python standard library. So I thank you for watching the video, and I'll see you in the next one. Till then, enjoy.